Hi, Xavier. As of now, the fan is not running, so just took a video for you. And I'll talk to you later, okay? Take care, buddy. Bye.
Krishna?
Yes, sir.
Yeah.
Sir?
You can start now.
Yes, sir. With warm greetings, I extend my warmest welcome to one and all invited here. This is Sai Krishnan pursuing my engineering degree in the Department of Electronics and Communication at Chennai Institute of Technology. We are analog beings living in a digital world facing a quantum future. Chennai Institute of Technology, the college, has not left any stones unturned in making its students worthy citizens. The time as a caterpillar has expired and the wings are ready. Yes, it is about transforming lives. It's been just 10 years since CIT has stepped in, but the victories are huge under the successful guidance of our Honorable Chairman, first generation entrepreneur Sri P. Sriram. It is indeed a privilege for all of us to get the opportunity of attending these webinars. To be short and crisp, yes, it is all about Knowledge 4.0. Today, we have our expert Dr. Xavier Fernando and our organizing secretary Mr. Eric Clapton. I feel much pleasure in welcoming you all. Now, I request our organizing secretary Mr. Eric Clapton to give a brief introduction about our session. Please, sir.
Good evening to all present here. I am very happy to welcome all of you to the one-day seminar on research challenges in sustainable IoT in the lens of 5G wireless network image co-segmentation under Knowledge 4.0 webinar series. This is one of the trend-setting and innovative initiative of Chennai Institute of Technology (CIT) established in the year 2010. Within the short span of time, we achieved top 10 position among 522 engineering colleges affiliated to Anna University Chennai. Knowledge 4.0 webinar series going in a very successful manner under the guidance of our Honorable Chairman Sri P. Sriram, the first generation entrepreneur, a well-known individualist and managing director of MK Group of Companies. We have been conducting various webinars under this webinar series, such as technical webinar, research webinar series, innovation webinar series, and career guidance webinar series. In addition to this webinar series, we have been also conducting FDPs, workshops, conferences, and seminars. Now we heartily welcome our today's expert, Dr. Xavier Fernando, Ryerson University, Canada, on behalf of Chennai Institute of Technology. He will deliver lecture on research challenges in sustainable IoT in the reliance of 5G wireless networks. I also welcome all the participants from all over India to this seminar and hope that you all will have a great time ahead. Now I will call upon Sai Krishna to introduce the expert. Thank you all.
Dr. Xavier Fernando is a professor at the Department of Electronics and Computer Engineering, Ryerson University, Toronto, Canada. He has authored over 200 research articles, 2 books, and holds few patents on non-disclosure agreements. He is the director of Ryerson Communication Lab that has received a total research funding of about $31,85,000 from the various governments since 2008 from industry and government. Information about the alumni of this lab is available at different links. He was an IEEE Communication Society Distinguished Lecturer and delivered close over 50 invited talks and keynote presentations all over the world. He was a member in the IEEE Communication Society Education Board Working Group on Wireless Communication. He was the chair IEEE Canada Humanitarian Initiatives Committee 2017 to 18. He was also the chair of the IEEE Toronto section and IEEE Canada Central Area. His research interests are in signal processing for optical wireless communication systems. He mainly focuses on physical and MAC layer issues. He has special interest in underground communication systems of cognitive radio systems, visible light communications, and wireless positioning systems. He has received many awards and recognition, which include the IEEE Communication Society Distinguished Lecturer for 2012 to 13 and IEEE Toronto Section Sustained Leadership Appreciation Award in the year October 2016. Now, without any further ado, I request you to take over the session, sir. Please, sir.
Yeah, thank you very much for the kind introduction. I'm going to start the PowerPoint. Can everyone see the slides?
Yes, sir, we can see.
Yes. Okay. So, good evening, everyone. My name is Xavier Fernando, and thank you very much for the kind introduction. So, as you would have understood from the introduction, I am basically a wireless communication person. I'm doing research and mostly in the communication systems and communication technologies. So today we will see uh, some of the aspects of IoT, Internet of Things, in the realms of 5G wireless networks. So it's a brief introduction about Ryerson University and my lab. I think it's already covered in the introduction, so I will go to the next. So, growth in Internet of Things and wireless sensor network, typically known as WSN, right? So this is a bit old side. You can see that there is a staggering increment in the number of objects or devices that are connected to the internet. And currently, we have about 26 to 30 billion devices connected to the internet. It's almost 5 times the world population. Right? World population is about 7 billion. So we see about too many devices are actually connected to the internet, forming this huge Internet of Things era. Okay. And the Internet of Things, the connected devices have numerous applications. Very few are shown here. It can be used in agriculture. It can be used in building management, in energy management, in embedded systems, so many various other day-to-day lives. And you also have lots of sensor nodes talking to each other, creating a machine-to-machine communication scenario, typically called the wireless sensor network. It's used in security and surveillance, smart cities, vehicles, especially in autonomous vehicles, telemedicine, healthcare, to say a few. And typically, I like to call these as 3 I's. Basically, we have instrumentation where we actually collect various informations using sensors, and then we have interconnection where all these sensors are connected and form networks, and we apply intelligent algorithms to make correct decisions from this collected information. So these 3 I's are actually part of the data sciences, which form the fundamental backbone for these IoT-based cyber-physical systems. Okay. And also a lot of people are now, we are moving towards Industry 4.0. So if you look the step-by-step evaluation of industrial revolution, basically the first generation industries were generated in the 15th, 16th century, basically mechanization and introduction of steam and water power. Then we moved on to Industry 2, where mass productions and assembly lines were introduced. Then we moved on to Industry 3.0, where production lines are automated using computers and IT systems, and some extent of robotics also was involved. But right now we are moving to Industry 4.0, which is basically represented by having smart factories and autonomous systems that are self-driven systems with Internet of Things, machine learning, artificial intelligence, and intelligent decision making. So we see that IoT is an integral part of Industry 4.0. And a lot of people talk about wireless sensor networks, WSN, and Internet of Things. So there is sometimes a little confusion between these two. So I want to clarify here. Wireless sensor networks are like the eyes of the Internet of Things. Because this is where you have lots of sensors, small wireless electronic nodes, which collect lots of information like mobility, location, sometimes even simple things like temperature, pressure, and various other parameters are collected by wireless sensors and transmitted. But all this collected information have no use unless you analyze that information and make appropriate decisions. Right? So that is where the IoT is coming into the play. So IoT, in a broad sense, is like a brain. So it stores both real world data and can also be used to monitor the real world parameters and give meaningful interpretation. That's the key difference. In IoT domain, you actually make decisions, analyzing the data collected by wireless sensors, and then make appropriate decisions and take action. Like, for example, braking a car, or slowing down an aircraft, or simply turning on and off lights. All these are actions that can be taken automatically by looking at the data and making decisions. So that is where the IoT, cyber physical systems, basically come into play. Okay, so let us look at brief history. Basically, we know the internet started in 1969, and in 1990, in 82, TCP/IP came into play. In 1990, the first device was connected to the internet that was not a computer. And only in 1999, they called it the Internet of Things, IoT. And after 6 years, it started getting global attention. And around 2008, the number of connections were huge. Actually, the IPSO was formed. And in 2011, after the IPv6 launched, so we all know that IPv6 enables huge number of addresses, because it is it enables, I believe, something like 16 trillion devices can be uniquely addressed using IPv6. Then it really gave a momentum to IoT. And currently, as you saw, that IoT is taking over. We have about 30 billion devices connected to the internet with unique IP addresses. And if you look at an IoT framework, as I mentioned earlier, we have sensors, actuators with IP address that can be connected to the internet and directly either collect data or do some action. And then we have local networks, because all these things need to be connected. So they can be connected through either wired or wireless, local area networks, LANs, body area networks, or personal area networks, control area networks, which are specific to vehicles. And there could be so many other networks. Even if you are looking at a smart grid scenario, they are connected using something called regional area network, even sometimes wide area networks. So you need networks to connect these devices, and then all this collected data need to be stored and analyzed. So that is where the cloud services come into play. So that data is either sent to or received from cloud, and analytics were performed. So after analyzing the data, certain decisions were made, and the decisions are transmitted to connected consumer electronics. So they could be autonomous vehicles or printers or whatsoever. So this is simply the IoT framework. And if you look at the architecture of IoT, in the first layer, we have physical devices and controllers, the things. And second layer is actually the connectivity, where these things are connected. And the third layer is edge or sometimes fog computing. So this is actually the data element analysis and transformation at the edge level. So we need to understand the terminology here. So if you have a smartphone, the smartphone is actually an edge computing device because that's at the user end. And cloud is in the central area. It's more like a central server. And fog is something in between. See, sometimes we have smaller servers that are directly connected to the end user and also connected to the cloud on the other side. So these fogs are in between the cloud and the edge. So we have this architecture: cloud, fog, and edge. Nowadays, a lot of computing can also be done at the edge, at the user end. And then you collect this data, storage at level 4, and data abstraction. So you basically aggregate this data and analyze it. Then you have the applications. So where you made the decision, you made the reporting, analytics, cloud analytics, and control. And eventually, we actually do a collaboration and process involving people, devices, and business processes where the whole picture is completed. Okay. So if you little bit closely look at the communication technologies of IoT, there are it's mostly wireless. Almost more than 95% IoT communication is through wireless means. So we have so many different wireless networks that are making these connections. So some of these are listed here, like Bluetooth Low Energy, BLE, Zigbee, Z-Wave, Blowpan, Thread, Wi-Fi, very well known, cellular radio, near field communication, Sigfox, Newell, LoRaWAN, etc. And if we have a close look of these wireless communication standards, we see a lot of times these Internet of Things have a trade-off between the distance it can cover, the energy it needs, and the bit rate. So those are the three key variables that are basically decide which wireless standard you will be using. So the graph here shows it. So if you look at the top, it's Wi-Fi. We know Wi-Fi can go up to even 1 gigabit, several megabit per second. So the data rate is very high, but the distance coverage is small. Also, we need to understand Wi-Fi consumes a lot of energy. So Wi-Fi is typically not a good solution if you are talking about low-powered wireless sensor networks. Wi-Fi is good for our internet access, but not for low data rate, low power connections. And then we have 4G LTE. Then we have the Bluetooth, Zigbee, Z-Wave, all these things that cover shorter distance with relatively low bit rate. And some of the two remarkable standards are actually Sigfox and LoRaWAN. LoRaWAN is not shown here, but LoRaWAN is also a very good standard that cover a fairly reasonable good distance, up to 10 kilometer or even more, with low data rate and low energy consumption. So these are typically preferred, again, depending on the application, which application you are talking about. And we have to remember a lot of these sensors are typically, they don't transmit very high bit rate. They transmit regularly or periodically, but a lot of times their bit rates need not to be that high. But their energy constraint is very high. They need to conserve their energy. So we need to cater the system accordingly. Okay, this is a typical application of IoT. So IoT in transportation. So they're saying that global market in IoT-based connected cars is expected to reach about 46 billion by 2020. This was a prediction made in 2017, but it is happening. I don't know exact value currently because a lot of things happened in 2020. Things changed, and because of the COVID and other issues, a lot of changes have happened in the last few months. But still, IoT plays a very important role, for example, in transportation sector. I will not go in detail in this slide, but it's understood that IoT will play a key role. Okay. So IoT in smart grid. So a lot of us electrical engineers are very familiar with power grid, and we know actually the power grid became smart grid like about 3 years back, because the old grid was unidirectional, where the big generators generate power and they are transmitted to users through unidirectional communication, only from the generators to the user. But later on, as people were interested in incorporating a lot of renewable small-scale energy resources, such as wind farms and solar panels into the grid became a bidirectional network, because users could also inject energy into the smart grid as well as they consume energy from the grid. And a lot of smart measurements or smart features need to be involved, need to be incorporated in these grids. So that's how actually the smart grid came into the picture. So you see, actually, we have different generations, smart generations, using either wind farm or solar cells, etc. And this energy is injected into the grid, and then we have several applications where we actually use the electricity energy to power up various devices and things at home. And also, electric car is an important aspect of actually smart grid that is also connected to this. So the IoT plays a very important role in smart grid. It can actually manage the energy usage. For example, here smart meters are very popular in the most developed countries, where actually the energy usage is automatically collected and transmitted without a manual human interaction. Basically, no need for a person to take readings. The smart meters automatically transmit data, and those are collected, and the user is billed. And the user also has an ability to actually see how effectively he is using the energy and what is the best way to use the energy. Say, for example, during off-peak hours. What are the things he could do in off-peak hours? Right? So all these things are possible when you collect information automatically and store that data and make it available for the user to look at. So that is all possible because of the integration of smart meters, which is a very good example of an IoT application. Right. Also, there are so many other things. For example, the utility companies, they want to ensure that the electricity generation is dynamically adjusted according to the usage. Right? And we know actually the electricity usage is a random process. Electricity usage keep fluctuating, and you have to keep adjusting your electricity during short-term forecast as well as long-term forecasts in order to ensure that the user is continuously getting electricity, uninterruptible electricity services, right? For that, they use this IoT-based collection of data and analysis of data and prediction models so that they can actually predict electricity need instantaneously in short term as well as in long term. So IoT is a very important element of IoT, smart grid. And here I have listed a few hardwares that could be used for IoT system development. For example, Raspberry Pi and Arduino are very popular platforms, and there are many others also listed here. You can have a look closely when you get more time. And also a lot of different software platforms that are used for development of IoT-based systems. And typically Python, C, C++, Java are the popular languages. And there are lots of platforms, for example, Samsung, and also I'm sure that IBM has their own platform, and so those are different platforms people can use. And also I have listed here some of the data compression standards, because as you know, a lot of time the data is compressed before transmission to ensure a more efficient transmission, not to occupy the communication networks, as well as not to occupy too much disk space. So these are all a lot of compression standards. I think you are very familiar with these standards. So let's go to the next. So 5G wireless networks. So we are in the entry point of a very big change in the communication world, the wireless communication world. That is the introduction of 5G wireless networks. So simply, if you look at 4G and before that wireless networks, typically these are characterized by having larger radio cells called macro cells. Typically has a radius of few kilometers. And there were also some small cells in specific areas like downtown areas or in shopping complexes, etc. But mostly it's predominantly macro radio cells and some advanced radio methods, right? And Wi-Fi connection and cellular networks are independent. They are not working together. And limited sharing of spectrum and frequencies typically for cellular services is about up to 2.5 gigahertz. And total spectrum usage is only about 1 gigahertz. That's typically the current wireless networks. And also I have to mention, typically the current speed, the current bit rates are in the order of at most tens of megabits per second. So if you get more than 10 megabit per second over your cell phone using a cellular data service, that's really, really good. Lots of time is less than 10 megabit. But now we know all over the world, many companies are working on these 5G networks, and in some places 5G trials have already started. And 5G is actually an interruptive standard. Like it is, some people call it a destructive standard, because actually it really changes the way the wireless networks have been operating. Because 5G actually is very backward compatible. It will also support 4G, as well as it will support Wi-Fi as well. So for example, 5G is actually supports heterogeneous networks. So it actually will support Wi-Fi as a part of 5G. Also, typically it has small cells, many small cells, many advanced radio methods such as smart antennas, massive MIMO, where you have hundreds of antennas in base stations, and the usage of both unlicensed as well as licensed spectrum, and selective sharing of spectrum with the government, frequencies up to several tens of gigahertz, up to 60 or even 100 gigahertz, typically called as millimeter wave bands, and total spectrum usage will be several gigahertz. And the speeds are expected to be in the order of gigabit per second. 1 or up to even 10 gigabit per second of bit rates over your wireless smartphones or wireless devices. So this is typically the envisioned 5G scenario, where, as I mentioned, it's a massive MIMO system where you have hundreds of antennas in base stations. So when you have hundreds of antennas, that enables a very accurate beam forming. So you can actually form beams and track users in real time, so that you can support very high bitrate connections to each user using beamforming and massive MIMO networks. Also, it will incorporate NFV, network function virtualization, internet, device-to-device communication, direct base station free device-to-device communication, relaying, and say typically small cells with gigabit Ethernet up to 60 gigahertz. It even has option to incorporate VLC, which is visible light communication. That's actually an optical means of communicating using LEDs, using solid state lights or LEDs for wireless communication. Visible light communication is a very interesting, fast emerging area, will be part of 5G wireless networks. And of course, it incorporates wireless sensor networks. And another aspect is cognitive radio networks, which I will talk a little bit more later. So all this makes the 5G concept is a heterogeneous network supporting multitude of technologies, providing many different services. So another very important aspect of 5G is called the network slicing. Because current radio networks, they don't care what kind of service we are asking for. For them, actually, it's either voice or data. All the data is treated almost in the same way in current wireless networks. But 5G has provisions to treat your data or your communication services differently. So if you want a mobile broadband communication, that broadband communication layer will be treated differently so that you can have actually broadband communication for entertainment and internet and other purposes. Say if you have massive IoT network where you have large number of IoT nodes, sensors that transmit low bit rate, but huge number of them, then they need to be dealt with in a different way. So they treat IoT devices in a different way for many different applications. And another important aspect of 5G networks is support to these autonomous vehicles. Because we know autonomous vehicles need very ultra low latency and ultra high reliability communication. Say, for example, if you are going to use cellular networks to transmit many mission critical data, then you have to have high reliability and few nanoseconds of latency, and this data need to be treated with high priority differently. You cannot combine data from autonomous vehicle with data from a small sensor, a passive wireless sensor. So they have to be dealt differently. So that is what we call the 5G network slicing. So 5G has the ability to actually treat different priority communication services differently. And then about security. We know as more the automation, actually security is an issue. So there could be some attacks such as routing attacks, malicious injection, denial of service attacks. Some of these are very well known. These are the attacks that are used to attack, and also security professionals developing various algorithms to overcome security and privacy issue. Right? Privacy is another major important issue when you have too much automation and too much communication and information technology in place. And cybercrime damage costs to hit about $6 trillion annually by 2021. And you can see from this pie chart, actually, United States is in the forefront of this cybersecurity business. And also China comes number 2. And I think India is somewhere here. It's about 3% contribution towards the cybersecurity. So it's a good area where India can focus more and do some more development. Okay. So a little bit about, I kept talking about autonomous vehicles and vehicular connectivity. So right now, actually, there are vehicular connectivity has become a very interesting and important application of IoT, Internet of Things, because all the vehicles in the future will have communication ability. They will have their own IP address, and they should be able to transmit lots of different information, including traffic data, collision data, emergency data, as well as non-emergency data to the network, and the data will be analyzed, and the vehicular traffic flow will be regulated using intelligent transport systems. So I'm going to talk about different communication technologies. Currently, they are using DSRC, dedicated short-range communication, as well as wireless access in vehicular environment, WAVE. These are prominent radio standards. And also they are using actually wide area 5G type cellular networks to get some of the data. And some of these vehicles also have these OnStar units that collect, save data, and transmit when needed. Okay. So when we move on from driver-based vehicle to autonomous vehicles, the connectivity and the amount of data you need to transmit become massive. So if you take a simple autonomous car, there will be about 100 electronic control units and about 100 million lines of code from different vendors, and you have to actually a way to incorporate all these sensors and transmit the data continuously in real time, so that you actually make lots of mission critical decisions: when to brake, when to accelerate, and whether you are going to hit a pedestrian or not, right? As well as if you have enough tire pressure, etc., etc. So many different information, and all this information need to be processed, right? And also let me move on to electric vehicles, which is actually another important upcoming application of this Internet of Things. When I talk about smart grids, I mentioned actually electric vehicles are an integral part of smart grid, because they take a big chunk of energy from the grid. Actually, an electric vehicle can need almost same amount of energy a small household will need per day if you are commuting about a standard distance of about 100 kilometers per day. So these electric vehicles are really important because the power grid operators need to provide enough power to these electric cars, and the electric cars also are ideal candidates for autonomous driving. If you remember, actually, that is why Tesla, the leading autonomous company, which currently actually bypassed the value of even Toyota to become the most valued automobile company in the world, is focusing a lot in autonomous driving to actually enhance their electric vehicles, because electric vehicles and autonomous driving go hand in hand. Electric vehicles are easy to control in the autonomous using autonomous technologies. And actually, this is a project we did in our university, because all these electric vehicles, when they are in the road, actually we don't know how much energy they consume. And Toronto Hydro One is a power company in Canada. They wanted to know how much energy. Actually, they wanted to get an understanding of the power usage of electric vehicles when they are offline in the streets. So actually, we developed something called a PEV manager. That's a plug-in electric vehicle manager. That's a wireless module that is attached to an electric vehicle that reads information from the vehicle, such as the state of the charge of the battery, the speed in which it's being driven, and the speed in which actually the discharging is happening, and the traffic conditions, etc. So it collects good number of data, and all this data will be transmitted to something called a PEV.com website where we develop. And this data is available for the user as well as to the Hydro One, which is actually the power company. So this was one of the projects we did in the past, and still there is lots of interest to actually collect data from these electric vehicles and autonomous for making various decisions. And the smart home. So actually, buildings in developed countries are really complex systems, because in these countries we typically have the heating, ventilation, and controlling system, HVAC systems, heating, ventilation, and air conditioning systems. And these HVAC systems need to be controlled currently, a lot of times they are controlled manually, but in future or in big buildings, they need to be controlled automatically. So actually we have heaters that will provide heating, and we have lighting control, and then we have home personal computers, etc. And we have this heater, cooler that are actually controlled by thermostats. And lots of time nowadays in houses, they are installing solar panels actually to generate a little bit of their own energy. And you need to monitor the amount of sunlight and optimize the energy injection from solar panel into the building. So these are typical applications of a smart home. And when you get to a big building, this becomes very complex. And this is another project that actually we did in Ryerson University. And we have been working on this, how to optimize various parameters, installing wireless sensor networks in buildings, and collect various data. Okay, so let me now come to the sustainability. So actually, when we're talking about sustainability, there are two things we need to focus. First, the energy. Because as I mentioned, these sensors make a big part of IoT. And a lot of time these sensors are installed without a connection to the power grid. They have their own battery supplies. And as you know, whenever you have battery, the battery is going to drain, and it's going to cause issues in wireless sensor networks. Dead nodes will severely impair the network performance, and periodic battery changing will be a costly exercise. Especially, say, if you take a smart home, we have about 300 to 400 sensors, various sensors you need to be installed in the house. And you can imagine, actually, even when you have one or two sensors, periodically changing the battery, ensuring these batteries, these sensors are in good operating conditions, can be a difficult thing. And when you have hundreds of sensors, it's even more difficult. So also, actually, discarding used batteries is an environmental problem. So when you have huge billions of sensors, and you are discarding billions of batteries into the environment, it can become a huge issue, right? So people are looking at different ways to avoid the energy drainage of these wireless sensors, energy saving, try to minimize the energy usage, but there is a limit how much you can reduce the energy usage. And energy harvesting, or actually self-generating energy, is an active area of research, and which I have also been working for some time. So basically, if you look at an energy harvesting wireless sensor, energy harvesting is the process of capturing ambient energy and storing it as electricity. And properly designed energy harvesting can provide a sustainable solution. Say, for example, when the energy drains, you actually collect energy, and typically you store that data in a storage device and then use it. So there are many different environmental energy sources you can use. I have highlighted few of them here that are most suitable for wireless sensor networks. Say, we can use actually thermal energy using thermoelectric couplers or thermoelectric generators. We can use sunlight or light in general using photovoltaic. And we can actually harvest energy using antenna, radio energy. Also, you can actually get energy through magnetic coupling using induction coils. And you can use pressure or mechanical movements using piezoelectric elements. So these are typically more appropriate for wireless sensors. And also, there could be other energy harvesting means that are suitable for some other applications. Right? So this table actually shows the energy density and from which source you can obtain them. I'm not going to go through all of them, but you can see typically the energy available from various environmental sources are very, very small. They are in the order of microwatt. they are in the order of microwatt. Okay, whereas the energy usage will be typically in the order of milliwatts or even more. We will look into that. So this slide actually shows a typical architecture of a energy harvesting device, where you actually typically you have a transducer where you convert the energy, the environmental parameter, light or pressure, into electricity, a small current, and then you actually have a power management circuit. Then you store it in a supercapacitor or a rechargeable battery, and then use it. So these are some of the projects I just want to quickly show. This is a project we did in Ryerson, actually, where it will enable safety for amusement riders when they are riding in like amusement rides that does not really have electricity supply, because they are up in the air, they sit in the chair, and the chairs will be rotating while they travel. So actually, in order to ensure their safety, we need to make sure they don't get up from their seats. So we had power sensors in their seats, and we actually had an energy harvesting circuit. So energy is harvested from the movement of this amusement car, and then whenever a user is getting up from the seat, actually we create an alert signal that will be transmitted back to the control center, so that we know that, and we want the user to actually sit back. And this is another project we did, where actually we were generating energy from the temperature difference between hot water pipe and cold water pipe in a typical house in Canada. Because we know actually in most developed countries, they have hot water supply as well as cold water supply. So a lot of time there is a temperature difference, gradients between these two pipes. And if you can, and these pipes actually run close to each other. So if you come up with a smart idea where you can have both electrodes of a thermal energy generator in these cold and hot water pipes, you can get a small voltage difference, and you can collect enough information, enough energy to actually run some wireless sensors that will monitor the quality of water, or the quality of or the temperature of the water, etc. It's another project. And also ambient RF energy. RF energy can be collected from the radio signals that exist in our environment, typically from television broadcasting, radio broadcasting, Wi-Fi. So this is another project we did at Ryerson. And typically RF energy does not need additional hardware, because you can use the same antenna to collect RF energy as well as for communication. So that's an added advantage. So there is a fundamental issue actually when you do this energy harvesting, because the harvested energy coming at it's actually a stochastic process. Because say, for example, if you are collecting energy from somebody who is walking, from the mechanical movement of a user, that's a random process. So a person is walking, you collect energy from his body movement. It's a random process. We don't know when he will walk. He will walk, right? And the energy consumption of most wireless nodes are shown here. Typically, when you transmit, your power consumption can be up to about 50 milliwatt for a short duration. And when you are not transmitting, it's about 1 milliwatt. And when you are sleeping mode, it's about 5 microwatt. So, as we saw earlier, the collected energy will be in the order of microwatt, actually. So you have to collect energy for a longer duration in order to support the energy usage or the wireless transmission for a short duration, right? So there is a mismatch between the amount of energy, the rate of energy you are collecting, and the rate of consumption. And the storage and power management need to actually manage these two different rates. So that is an important aspect of the energy harvesting systems or energy harvesting IoT devices. The other thing is actually the causality constraint. You cannot use energy before collecting it. There is no credit system here. Right? You have to wait until you have enough energy in order to use that. So that will impose certain additional constraints in routing and other algorithms in energy harvested wireless sensor networks. Also, these energy storage devices, I'm not going to go through all of them. Typically, we use rechargeable batteries or supercapacitors. Supercapacitors give you rapid discharge, while batteries have actually more slow discharge, but their energy storage density is high. And actually, I think its time is up, so I will quickly go through. The other sustainability issue is actually spectrum. The spectrum usage of these billions of devices. Right? There are a few standards shown here. They actually see how you can effectively provide radio spectrum for this upcoming huge number of wireless sensors, right? And cognitive radio is actually an interesting aspect where you use the spectrum of licensed spectrum in an opportunistic manner. You use actually when the licensed user is not using. That's cognitive radio networks. So in cognitive radio systems, you actually sense the existing spectrum, and then you access whenever it is not used, and that in that way you can actually coexist with an licensed user. Okay, an interesting application of cognitive radio system is actually aerospace industry. Say you have an aircraft, there are so many different wireless communication links nowadays exist in aircrafts, and they are using this cognitive radio technology where actually each electronics device, it uses which spectrum is safe to use so that it will not interfere with the electronics of the aircraft engine, so that it will cause any harmful interference with the aircraft functionalities. Okay. So that concludes my talk, and thank you very much.
Yeah, thank you, sir. Session was very interesting, and the participants learned a new technology in this. So we'll take up the questions. Then participants, if you have any questions, kindly post. We have one question, sir. Is 5G technology covers privacy issue?
Yeah, it's an open-ended question. Actually, the privacy, we need to understand. Privacy issue will never be 100% be covered, right? Everywhere, they develop several algorithms to ensure privacy, but it all depend on depend on so many issues. Because when you say privacy, we need to understand many these wireless service companies, say for example AT&T or any other Apple in United States, as well as service providers in India, we have a legal requirement to actually share the user data with the government if it is required. Right? So
Yes,
actually we have to be very, very careful which wireless company is installing our 5G network. Right? I know in India currently, a big company from an unwanted country is actually doing a lot of 5G network installation and 5G network deployment. My personal opinion is we have to be very, very careful with these companies, because a company from an enemy country should not have access to our wireless networks. No way. Because the data can always be compromised. You know what I'm talking about, right?
Yeah, sir. So one more question. Is Raspberry Pi enough for connecting medical devices through IoT?
Sorry, say it again.
Is Raspberry Pi enough for connecting medical devices through IoT?
Raspberry Pi is almost like a computer.
Yeah.
You can actually, my students, they work on Raspberry Pi. I don't directly work with that, but in my understanding, Raspberry Pi is almost like a computer. You can do pretty much everything you do with a computer, except for that it's not using Windows operating system.
Okay, whether IoT is applicable in power system optimization problem?
Exactly. I talked a lot about that. IoT is a very good tool for power system optimization because it can actually collect huge amount of data like about from the power generation of microgrids as well as power generation from macro grid and the bidirectional power flow as well as power forecasting and load prediction. All these things can be done by analyzing power usage data and generation capabilities, and IoT is a great tool for power system optimization.
Thank you, sir. When 5G in commercial markets?
It is coming. I mean, nobody can tell exactly, because actually we don't know. Things have changed a lot during this 2020 because lots of companies that were about to install 5G trials and 5G experiment systems have actually delayed that project because of this COVID scenario that we have right now. But it will happen soon. It will be a natural thing. I mean, it will always happen, but depend on the economic situation of the country and the need. And another thing is the commercial aspect, right? Because 5G is a great technology, but unless you have applications that will generate revenue and you are willing to pay for 5G technologies, then the deployment will not be that fast, right? But already 5G is installed. Actually, I think already has a 5G operating network in Korea, in South Korea, as well as in North America. In few places, they have this massive MIMO base stations and 5G trial networks.
Okay, sir. I think that's all about question. So thank you, sir. Thank you very much for accepting our invitation. Your session is very useful for our participants. Thank you very much, sir. We will meet once again any other occasion, sir. Thank you. Sir?
Yeah.
Thank you very much, sir. Thank you. We can close this now, sir.
Okay. Okay. Thank you. Bye.
Thank you, sir. Bye.